Alright, so till now we have learned that big O gives us the upper bound, omega gives us the lower bound, and theta gives us the average bound of the function, average time of the function. Now let us look at the formal definitions. Let's consider this graph. In this graph, fn represent the function whose upper bound we want to find. As told earlier, the x-axis represent the length of the input or the size of the input, and the y-axis represent the time or the space taken by the function. So if this function represent the time, then the y-axis will be the time, and if this function represent the space, then y-axis will be space with respect to the size of the input, which is the x-axis. The function gn will be called the upper bound of function fn if we can find a constant c and another constant n0 such that the function fn is always, the value of the function fn is always less than equal to c into gn. And this should be true for all the values of n greater than or equal to n0. You can see this n0 here. So after this value of n, you see that fn is always below gn. Before this n, there may be some value of n for which fn is greater than gn or fn is less than gn. So we will ignore all the values of fn which are before this n0. But after this n0, gn should always be above fn, which means that when this constant is multiplied to gn, it should always be greater than fn. Let us take an example. Let us say that the function fn is equal to 2n plus 3. So the graph of fn will be something like this. This is n and this is fn, and the graph will be like this. So this is 2n plus 3. If I take another function gn and I say that gn is 3 into n, so the graph of gn will start from probably 0, 0. Let us consider the values of fn and gn for certain values of n. If n is equal to 0, then fn will be, this is let's say f and this is let's say g. So if n is equal to 0, then fn will be 2 into 0 plus 3, which is 3, and gn will be 0. So 0, 0 here. For n is equal to 1, fn will be 5 and gn will be 3. So let's say here. So this is 5 and this is 3. For n is equal to 2, fn will be 7 and gn will be 6. So gn is getting closer. So gn is here and fn is here. For n is equal to 3, fn and gn are both 9. So they both becomes equal. I'm unable to draw this as a straight line, but you can see that it will be a straight line. So when n is equal to 3, at that point both fn and gn are equal, and for every value greater than 3, gn will be greater than fn. Therefore we can conclude that fn is big O of gn, or gn is the upper bound for fn. Can we say that if gn is equal to n, then also fn will be equal to gn? Probably yes. Then the constant will be 3, and we know that for 3 constant, c into gn will be greater than fn for all n greater than equal to 3. So if fn is 2n plus 3 and gn is n, then we can say that fn is big O of gn. Another way of finding the upper bound is that whatever function is given to you, you just ignore the constant of that function and ignore the constant multiplier and keep the highest value of n. So if fn is 3n square plus 2n plus 5, then I can say that gn can be n square. Or we can say that 3n square plus 2n plus 5 is big O of n square. The upper bound of any function is the highest power of n inside that function minus all the constants. And if you want to find the constant c, then c will be just 4. In this case, c can be just 4. So if gn is 4n square and fn is 3n square plus 2n plus 5, So the line of Gn may start below Fn, but it will ultimately come above Fn. And then it will remain above Fn. So Gn will provide the upper bound of Fn after a certain value of n. Let us see how is it useful in coding. Consider the function of linear search again that we discussed in the previous video. Let us assume that you want to make an entry in the log table every time you call the linear search function. So it will be something like this. Let's assume that there is a class by the name log which has a function called make entry, and this function is writing into the database. So if this function is writing into the database, it is taking some time. It may be taking substantial time, but this time is constant. And this for loop is the only loop which is dependent on the input value, which is dependent on the size of the input. So because this for loop depends on the size of the input, the time complexity of this for loop is order of n. And because this entry into the log takes constant time, so we can say that this is just some constant, C1. Therefore, the function that represents the time of this linear search will be this constant C1 plus some other constant into n. You may want to add some extra constant for this return statement and this initialization statement. But ultimately, it will be some constant into some other constant into n. We can conclude that this function is big O of n, or this function is order of n. So the proportionality that we discussed in the previous video meets the time complexity that we are discussing right now. When we say Fn is big O of n, this big O of n is actually the minimum possible upper bound. We can also say that Fn is big O of n square, because the graph of n square will obviously go above the graph of n only. We can also say that Fn is big O of n cube. We can also say that Fn is big O of n log n, and so on and so forth. Let us look at this graph again. From the same graph, we can conclude that Gn is equal to 5 into n square is also big O of n. We can also conclude that 6 into n cube is also big O of n, also big O of Fn. So all of these functions are upper bound for function Fn. So when we say upper bound of a function is not just one function. The big O of Fn is a set of all the functions Gn. For every Gn, there exist two constants C and n0, such that Fn is less than or equal to C into Gn for all possible values of n greater than equal to n0. So this is little mathematical, but I hope you should be able to understand it. Now this big O is a tighter bound, because here we are considering the equality also. If you remove this equality and consider the set of all the functions Gn, such that for every Gn there exist two constants C and n0, such that the function Fn is strictly less than Cgn for every value of n greater than equal to n0. Now, if you put this condition of strictly less than, it means you cannot have a possibility of Fn and Gn being the same. So if you make this definition a little tighter, then this will become the definition of small o. Therefore, the definition of big O is greater than or equal to, whereas small o is strictly greater than. And that's why I said in the beginning that even though there are 5 notations, only 3 of them are important. Because in a sense, small o is already contained inside big O. Because small o of a function is always a subset of big O of that function. Because small o of a function is always a subset of big O of that function. Now let's move to omega. The way big O was providing an upper bound to a function, omega provides a lower bound to the function. So the function Fn will never take time less than Cgn. If you want me to write the formal definition, then Fn is omega of Gn if there exist two constants C and n0. And when I'm saying two constants, I mean two positive constants only. So Fn is omega of Gn if there exist two constants C and n0, such that Fn is always greater than equal to Cgn for all the values of n greater than equal to n0. And now you can guess, if you change this greater than equal to strictly greater than, then instead of omega, it will become little omega. So a function fn will be called little omega, this is the sign of omega, little omega of gn, if there exist two constants c and n0, such that fn is strictly greater than cgn for all the values of n greater than equal to n0. So omega is closer to fn than little omega, and little omega is a subset of omega, the way small o was a subset of big O. Now let's come to theta. Theta provides both upper bound and lower bound. If you have a function fn, let's say fn is 2n plus 3 and gn is n. So we can find two constants c1 and c2 such that, let's say c1 is 1 and c2 is 3. So c1 into gn will always be less than equal to fn, which will always be less than equal to c2 into gn for all the values of n greater than equal to n0. It means that after a certain value of n, we can find two constants. When you multiply one constant with the function gn, it will always go below fn, and if you multiply another constant with gn, it will go always above fn. That way theta is a much tighter bound than big O and small o. And you can argue that we should be finding theta complexity instead of upper bound or lower bound. Your argument may be right, but in the industry, our focus is mainly on the upper bound. In the coding interview, our focus is only on the upper bound or the big O. But even in the upper bound, we provide the tightest upper bound possible, which means that we provide the minimum value of the upper bound. For example, so even though I say that the time taken by linear search is big O of n square or n cube or n raised to the power 4, and all of them are correct, in the interview, we will focus on the minimum of these values, which is big O of n. So in the interview, we will always say that linear search takes big O of n time. And that makes sense also, because we want to find the minimum upper bound, the minimum time taken by my function in the worst case. That is what we want to find. So this was all about asymptotic notations. Thank you.